All right, guys, so we are now talking about section 4.2. And we just got done making a big laws of exponent chart. And what I want you to do is at the bottom of that chart, I want you to add your fifth law. It's called the power rule, okay? The power rule. In fact, I like to call it the power rule, okay? And the thing with this is everything in the parentheses receives the power, okay? And it's through multiplication, all right? The hypothetical on this, we're gonna go back to the hypothetical, that's a Y there. Hypothetical on this is A to the N, okay, to the M equals A to the N times M. This one rule, it's easily recognized because, you know, we have parentheses, okay? And it ultimately, we are raising powers or exponents to greater powers or exponents, okay, through multiplication. Examples, and we're going to have lots of them, examples, okay? You know, 2x, in fact, let's do this first. Let's go really simple. X to the second to the third equals x to the 2 times 3, which equals x to the 6. Let's go and do our myth buster right here. It's not really that big of a myth. X to the second, you know, if we take it to the third, that's going to be x to the second times x to the second times x to the second. We already know, according to the product rule, that that's x to the 2 plus 2 plus 2, which equals x to the 6. But if you want to break that down, each one of them, it'd be x times x, x times x, x times x, all from being multiplied. We said when everything's being multiplied, we change the little number, it's x to the 6th. Or you can just take the shortcut, which is much nicer. Let's do another example here. Let's take 2x to the third y over z to the 5th, all to the third power, okay? You're gonna see a problem like this possibly in your homework. And in this instance here, we're gonna end up where everything in the parentheses receives the power. Now, again, I want you to understand everything, including the big number, okay? It has an exponent of 1. Y has an exponent of 1. Again, both silent ones. We'll put them in red there. So in essence, this is 2 to the, and I'm going to go ahead and grab my blue pen here. This is 2 to the 1 times 3. Then we're going to have x to the what? 3 times 3. Y to the, we'll have 1 times 3, because it was to the 1, all over z to the what? You got z to the 5 times 3, okay? Z to the 5 times 3. In the end here, we end up with 2 to the third, x to the 9th, y to the third, all over z to the 15th. Can we change 2 to the third to 8? Absolutely. Sometimes they do that. They call it 8x to the 9, y to the third, over z to the 15th. Both these are correct. The rule of thumb in the book is if you can do it in your head, they'll often do it. If you can't, like if it's 2 to the 15th, they'll leave it as 2 to the 15th. It's 2 to the third, they'll multiply it out. 2 times 2 times 2 is 8. Okay? You'll see those answers in the back of your book. It'll be easy for you to decipher. We're going to pause for just a second. All right, guys, let's just do a couple more examples. We're giving you more challenging stuff here, but so we have a parentheses, right? And parentheses is our indication. If you have a parentheses being raised to a power, and the stuff in the parentheses also has exponents, this is the power rule. You're raising powers to powers. And ultimately, everything has a power because at least it's the power of 1, as we see there. Notice that the parentheses is being raised to a negative power. It's going to end up being a to the 4 times negative 2 over 3 to the 1 times negative 2. In the end, that'll be a to the negative 8 over 3 to the negative 2nd. Well, we're not okay with negative exponents. We said we've got to simplify these. And so the 3 to the negative 2 is going to come up top, become 3 to the 2nd. A to the negative 8 is going to come down bottom, become a to the positive 8th. And 3 to the 2nd, that's definitely one we can do in our heads. 3 times 3 is 9. So it ends up being 9 over a to the 8th. And that is your final answer to that problem. Let's do this one right here. This one here, again, my recommendation on any of these examples is pause, do them, see if you can come up with it on your own, and then see how we do this and if you can arrive at the same answer. Again, we have a silent 1 right there. This is going to be 2 to the 1 times negative 3, b to the negative 2 times negative 3, over c to the 3 times negative 3. Well, interestingly enough, 2 to the 1 times negative 3 is obviously 2 to the negative 3, but this one, the negative makes it positive. This becomes b to the positive 6th over c, ahead of myself here, c to the negative 9. 2 to the negative 3 is going to come down, okay? What about b to the 6? b to the 6 is going to stay there. It doesn't have a negative exponent, so it gets to stick around. So we're going to end up with b to the 6th, c to the 9th comes up to the top, okay, over 2 to the 3rd goes down to the bottom. So I'm going to rewrite this here just so you see this. So right now, the c to the negative 9th is going to come up top, and become positive. The b to the 6th stays in its place, and the 2 to the negative 3 goes to the bottom, becomes positive. 2 to the 3rd, definitely one we can do in our heads. It's going to be b to the 6th, c to the 9th over 2 times 2 times 2 is 8. That is your final answer. Let's do one more easy one. Let's do one more easier one. What if I have 3x squared y to the negative 3 all to the 3rd power, okay? Everything in the parentheses receives the power, including the coefficient. Remember, that's to the 1 power. So this is going to end up being 3 to the 3rd, x to the 2 times 3, y to the negative 3 times 3. 3 to the 3rd, if you want to call it 27, you can. It's not 9, though. Remember that. 3 times 3 times 3, 3 times 3 times 3, that is 27. X to the 6th, and y to the negative 9. Can we have that negative exponent? We cannot. So this is going to be 27. And x to the 6th, staying on the top of the fraction, but y to the 9th going to its opposite place. Y to the negative 9th going to its opposite place, becoming positive. That's your final answer. Okay, good luck with that. So part of the homework is, the first part of section 4.2 is just the power rule. And that's going to be 1 through 51 odd. So the power rule 4.2 is 1 through 51 odd. There's more problems. We're going to cover scientific notation. That covers the rest of that section. We're going to pause for just a second. Go. Okay, guys, welcome back. Okay, so in section 4.2, the second thing we're going to talk about is an arithmetic principle, not an algebraic principle, an arithmetic principle that you might have learned a long time ago. It's called scientific notation. First thing I want you to understand is scientific notation is a way that we can express really, really, really big numbers or really, 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 really small numbers without sounding like complete morons, okay? So for instance, this number right here, 602, let's see, 1, 2, 3, 4, 5, 7, 8, 9. Okay, so that is a real number in the real world. It has significant value. This is a number in science that is used quite often. If we came to this place right here, we know that's the thousands place. We know that's the millions. We know that's the billions. We know that's the trillions. You know, and then I don't even remember. There's quadrillions. There's all kinds of names of numbers, and you know you can memorize them. But it's kind of like muscles. You know, use it or lose it, right? And we don't really use these terms, you know, past the trillions at this point in our lives. Maybe when you guys are my age, you know, the national debt will get you into another realm of numerical values, and you'll memorize that name. But to truly convey this number, what we do here is step number 1, and this is basically the definition of scientific notation is wrapped up in how to put a number in scientific notation. And the first thing we're going to do is we're going to move the decimal so there's only one digit to the left of it, but that digit cannot be 0, okay? And so here's our decimal right here. And we're going to count, not zeros, not zeros. That's a big misconception. We don't count zeros, we count decimal places. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Help me, Alex, 19, 20, 21. Do I stop here?
Nope.
Nope. Here?
Nope.
22? Yep, right there, 23. We went 23 places, so that's 6.02. So now, if you notice, I moved the decimal, so there's only one digit to its left, okay? And that digit cannot be 0, and it's not 0. And then the next thing is we're going to write our new number, okay? And that's our new number right now. Instead of 602, blah, 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 zeros, we have 6.02, but it's going to be times 10 to the n, and n is the number of places you moved the decimal, okay? And so, if you remember, we went times 10, we moved it how many places? 23. Okay, so 10 to the 23rd. That number is a scientific number called Avogadro's number, for those of you who are familiar with that. It's the number of molecules in a measurement called a mole, M-O-L, not the pointed nose creature, okay? If I have 0.0000006921, really small number, and I want to put that in scientific notation, again, I'm going to move the decimal, okay, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Do I go 9 and 10? No, it's not about numbers to the right. It's the number to the left of the decimal. This is 6.921 times 10 to the, how many places did we move? 1, 2, 3, 4, 5, 6, 7, 8, 10 to the 8. But this is called negative 8. And we're going to talk about that right now because this is step number 3. You must determine if n is positive or n is negative, okay? Now, there's 2 ways to do this, okay? N is positive if you moved the decimal left. And it's negative if you moved the decimal right, okay? And so, but another way is another way to think about this is if your original number was greater than 1 or if your original number was less than 1. Think about that. This number was much less than 1. That number is much bigger than 1. Sometimes that's an easier way for people to memorize it. Either way, it works, okay? All right, so that's how we put numbers into scientific notation. Let's come to the far right board here. If we have a number like, 12, well, let's do this. If we have a number like, yeah, let's do this. 1.2 times 10 to the 5th. And I tell you to take it out of scientific notation. Well, we're going to take 1.2 and we're going to move that 5 places. And we want this number because it's positive. Do we want to go left or right? Well, in this instance, we want the number to be bigger than 1 at this point. If we go to the left, it's going to be less than 1. That would be a negative value. So we're going to go to the right here. We're going to go 1, 2, 3, 4, 5. And I like to use this loop-de-loo method because then you can fill in all the loops with zeros and you end up here with 120,000. So 1.2 times 10 to the 5th is 120,000. In your homework tonight, you're going to be asked to put numbers into scientific notation and to take them out of scientific notation. You're also going to be required to do something that we call multiplication/division in SciNot. Okay, that's my quick abbreviation for scientific notation. You say it fast, sounds like snot. Okay, so here's the deal. If I have, let's say, 3.0 times 10 to the negative 12 over 6.0 times 10 to the 20th, okay? Before we do that, I want to draw your attention to something interesting. Come back here. What's that? It's a negative exponent. I thought we said we couldn't have them. There's one exception, right? There's always an exception to most things in life, right? So the exception of negative exponents is when we are communicating really small numbers in scientific notation. If we are in scientific notation, we accept negative exponents. We're not going to convert that. We're not going to call that 6.921 times 1 over 10 to the 8th. And we'll never do that. So don't go there, okay? We stick with that, all right? Only in scientific notation. Come back over here. So in these kind of problems right here, step number 1, we're going to take the numbers and we're going to do our work with their numbers, and then we're going to take the base 10 and we're going to do our work with the base 10s. What that means is we're going to kind of take a saw here and we're going to cut this, And we're going to just deal with, we got 3.0 over 6.0, put it in a calculator, you get 0.5. Then we're going to take 10 to the negative 12 over 10 to the 20th, and we're going to have 10 to the negative 12 minus 20, because that's the loss of exponents, which is going to make, and we can drop this times, we cut it and it just drops down, we can drop that times down into the answer here. It's going to become 10 to the negative 32. And we said we're okay with the negative exponent here. But what's going to happen in some of these problems where they're multiplying or dividing numbers that are in scientific notation is that answer is not in scientific notation. And the reason it's not is because, remember, there can only be one digit to the left of the decimal, but that digit can't be 0. And right now it's 0. So I want to show you this really interesting. Watch this. 0.5 times 10 to the negative 32nd. Forget about this right now, okay? Just forget about this right now and focus on this. If I asked you to take 0.5 and convert it to scientific notation, you would move this one place. You'd call it 5.0 times 10 to the negative 1 because you moved it one place and the original number was less than 1. Now if you drop this down, you have times 10 to the negative 32. Now if you combine those two, you have 5.0 times 10 to the negative 33. And this is the true answer. This must become this. Some people say, Brother Rich, why did you do all that complicated crap up here, like where you converted this to this? Why didn't you just add 1 to that? Well, really, if we truly added 1 to that, it'd be 31. You got to understand, you got to convert this and then combine the base 10s because they have the same base. You can combine their exponents. So if you can do it in your head, go for it, but I like to show my work because it works out better. Give you one last example. If I have 2.3 times 10 to the 5th, and I multiply that times 4.6 times 10 to the 15th, okay? You got a calculator on you? No? All right, I need you to do 2.3 times 4.6. So, oh, you got it? You do that. So we're going to end up with, here again, numbers with numbers. We're going to take 2.3, and these are being multiplied, times 4.6, and we're going to have 10 to the 5th times 10 to the 15th, because everything's being multiplied here. So we do the numbers first, okay? What's 2.3 times 4.6?
10.58.
10.58, and this is times 10 to the 5 and 15, same bases, so we can add their exponents, makes 10 to the 20, right? Because the base doesn't just have to be a variable. In this instance, it's a number. And 10 to the 5th and 10 to the 15th make 10 to the 20th. So again, is this in scientific notation? It's not. So we're going to have to move this one place, call this 1.058 times 10 to the 1. That's what that would make right there, because we moved it one place. Original number was bigger than 1, which is already times 10 to the 20th. These can combine because they have the same base. We end up with 1.058 times 10 to the 21st, okay? One last thing I kind of wish I would have shared with you guys in the last section. It's this principle right here of this. 2 to the 5th, okay, times 2 to the 7th. Alex, let's go ahead and pause for just a second. So this concept, I kind of wish that I highlighted this, and I just thought of this right now, is that, students, what they often do with stuff like this is they say, oh, that's, 2 times 2 is 4, and 5 times 7, or 5, let's say it's 4 to the 12th or something like that. Listen, you got to understand, that's not a 2, and that's not a 2, okay? This is a 2, and that's a 2. That's 2 times 2. But that's 2 to the 5th, which is 2 times 2 times 2 times 2 times 2, which is 32. That's not 2, it's 32, okay? And that is 128 right there. 2 to the 7th is 128. Okay? So what I want you to understand is the 2's are the base. And now you add the exponents, you end up with 2 to the 12th. Okay? You gotta remember that. You don't just have to have a variable to have a base. You guys have a good one. Talk to you later.